talked about the boundary layer equation in the last class, and those equations we were solving for flow over a flat plate. Okay, that is called Glacier solution. Okay, and the basic idea in Glacier solution was, I'm just reviewing a little bit. So if this is a flat plate and you have flow over it, so boundary layer develops, and velocity profile, which is like this. So outside it is u infinity. Let us say this is y-axis and this is x direction. So you can write u is velocity in x direction over u infinity. This is a function of y over delta. Okay, we can write it like this. Okay, and this is called actually a similarity solution, because what you are saying is velocity profile is similar. You look at this x location, velocity profile is like this, and you look at another location, velocity profile is like this. They are similar in the sense u over u infinity is a function of y over delta. Okay, and this y over delta, actually in the last class I wrote y over delta is eta. Actually it's not eta, it's a small correction. Y over delta is proportional to eta. Okay, so you can say u over u infinity, which is a function of y over delta, you can say this is a function of eta. Okay, so y over delta is not eta, it is proportional to eta. Okay, okay, and then based on this, actually the partial differential equation, that momentum equation, which is a partial differential equation, that becomes an ordinary differential equation. Okay, and you have boundary conditions. That equation can be solved. There is no analytical solution, but numerically you can solve. And by solving that equation, you get f and f prime. Okay, these functions, what these functions are as a function of eta. That is the solution of those equations. And these things give you what is the velocity profile. So effectively you got the velocity profile, and that is what we were looking for. Okay, so once you have velocity profile, we can write down what the boundary layer thickness is. We get that also. You get delta equals 5x over square root of Reynolds number x, where this Reynolds number x is rho u infinity x over mu. Okay, that is Reynolds number x. Okay, so this Reynolds number based on x. Okay, so now see this equation, it's applicable for a flat plate. We are talking about flat plate and laminar flow. Okay, so let me write it as delta over x equals 5 over square root of Reynolds number x. Okay, let us examine this a little bit. Okay, now this flat plate, okay, let us say its length is L. Okay, so the maximum boundary layer thickness is here because it grows, and say it was laminar throughout. This is maximum at x equals L. Okay, so you can write delta max, this is maximum boundary layer thickness, which occurs at x equals L over L, equals 5 over square root of Reynolds number L. Okay, and let us now consider some values. Okay, if Reynolds number, this REL, is 10 to the 4, okay, what will be this delta max over L? Actually you will see, so this will become 100, delta max over L will be 0.05. Right? It will be just 0.05. Okay, so see the maximum boundary layer thickness in comparison to the length of the plate is 5%. Okay, so can I call it thin? say this is 5% of the length of the plate. Okay, so you can call it thin, it's fine. Okay, so it's fine because the boundary layer equations, those are based on the assumption that boundary layer is thin. So eventually you want to also see, okay, when boundary layer is thin. Okay, so if Reynolds number is high, like I gave the number 10 to the 4, then boundary layer, the maximum boundary layer thickness is 5% of length of the plate, so it is thin. Okay, so now this is fine that you say that the boundary layer is like this. The effect of viscosity is confined to this region. In this region, the effect of viscosity is there, and it is confined to this thin layer, and outside, okay, although the viscosity is there, like fluid has its viscosity, but there is no effect of viscosity because there is no velocity gradient there. Okay, so the flow is inviscid. Okay, that is basically what the boundary layer is. You divide the flow into two regions, inviscid flow and a flow and a region in which viscosity is important. Okay, let us take some other number. If Reynolds number is, let us take a small value, say just 100. If it is 100, then what will be delta max over L based on the formula we have?
50%.
Okay, it will be 50%, right? It will be 0.5, so 50%. Okay, so this is not thin. Okay, it is thick. So actually this formula will not even be applicable because this is applicable for a thin boundary layer. Okay, so this won't be applicable, but at least we get the idea that Reynolds number is small, that boundary layer is thick. So if you draw the flow situation, so this is like this. Okay, now you can say that I'm drawing it like this. This is the region, it's a large region around the plate in which viscosity is important. Okay. And this is the region in which the flow is inviscid. Okay, so the boundary layer theory is not valid, okay, because it is too thick, this large region. Okay, even ahead of the plate, in this region also the effect of viscosity will be there. And if you want to draw streamlines, say streamline here. Okay, so the flow is in this direction, but because of the boundary layer, there is deflection of the streamline, you know that. And in this case, because boundary layer is thick, the deflection will not be negligible, it will be substantial. Okay, so it is going to deflect like this, it will be substantial. Okay, whereas if the boundary layer is thin, the deflection of this streamline is very small. Okay, it almost goes straight. Okay, so that is the idea. So this equation is important. We got this boundary layer thickness. And in the last class, we also got this expression that CF, this is local friction coefficient, is 0.664 over square root of Reynolds number X. Okay. And you know how this local friction coefficient is defined. It is local shear stress at the wall over half rho u infinity square. Okay, so we have that also. So that is what we did in the last class. Okay, and you also see that this CF varies with x to the negative half. Okay, and boundary layer thickness delta varies with x to the half. Okay, that is the way it grows. Okay, it grows with square root of x, and the friction, local friction coefficient, that decreases. Okay, as boundary layer thickness increases, it decreases because this is related to the velocity gradient at the wall. Okay, shear stress is related to the velocity gradient at the wall, that decreases as boundary layer thickness increases. Okay, now we will focus on energy equation. And for energy equation also we can do the similar thing what we did with the velocity profile. Okay, so let me draw that. So this flat plate, and now this represents thermal boundary layer. Okay, this is not velocity boundary layer, this is thermal boundary layer, and at any location, say at this location x, okay, I'm showing temperature distribution like this. If temperature at the surface is Ts, temperature of free stream is T infinity, and say Ts is less than T infinity. Or let me take it greater than T infinity. So, okay, let us say surface temperature is greater than T infinity. Then temperature distribution is like this. It is T infinity outside the boundary layer, and then within the boundary layer it increases. Okay, it is like this. So we show it in this way. Okay. Although temperature is a scalar, but it is convenient to show it like this, that with respect to this reference, the temperature of the wall is at this point and temperature of fluid is at this point. Okay, so we show it in a sort of pseudo vector, although it is actually a scalar. Okay. Now if I write down T star equals Ts minus T over Ts minus T infinity, then the profile of T star will be like this. You can verify this. T star will be 0 at the surface and it becomes 1 in outside the boundary layer. So this is profile for T star. It is 0 here and it becomes 1. Okay, so it is analogous to velocity profile. Right? Okay, velocity becomes from 0 to u infinity. Okay, so you can say that the profile for T star, okay, which goes from 0 to 1 within the boundary layer, this is also some function of eta. Okay, eta goes from like right, just like velocity. Okay, we can say that. Okay, and now based on this we can modify the energy equation. Okay, that equation you have already. If you want me to write down again, that equation is u del t del x plus v del t del y equals alpha del square t over del y square. Okay, this is the equation. In this equation we can substitute for u, v and these temperature gradients. Okay, and you end up with this equation, which is again an ordinary differential equation. Okay, that equation is d square T star over d eta square plus half Prandtl number times f dt star over d eta equals 0. Okay, get this equation. Okay, where the boundary conditions are, see, this is an ordinary differential equation and the boundary conditions are T star at 0 is 0 and T star at infinity is 1. Okay, those are the boundary conditions. Okay, and this equation also can be solved numerically for different values of Prandtl number. See, we already have solution for f. Okay, that was based on the solution for the velocity profile. We already have f, and for different values of Prandtl number we can solve this equation numerically, and I'm just going to plot how the solution looks like. So if you plot eta versus T star, so T star goes from 0 to 1. The solution looks like this for different values of Prandtl number. Okay, when Prandtl number is 1, it is like this. So this is for Prandtl number 1. Okay. For Prandtl number 7 or any number, if it is greater than 1, profile is like this. 7. And if it is less than 1, say Prandtl number is 0.6. 0.6. Okay, so for different values of Prandtl number we got what temperature profile is. Okay, that's all we needed. Once you have temperature profile, you can find out how much is the thermal boundary layer thickness, right? The point, the location at which T star becomes 0.99. that is the thermal boundary layer thickness. And we can also get what is the gradient here, temperature gradient at the wall, dT star over d eta when eta is 0. Okay, that is temperature gradient here. Okay, I'm skipping some of the steps, but just giving you an overall idea, okay, how you work with these equations. Okay, it turns out that this dT star over d eta at eta equals 0, we get this from the solution, is 0.332 times Prandtl number to the 1/3. And this is applicable when Prandtl number is greater than equal to 0.6. Okay, you get this correlation for dt star over d eta. Okay. Now, convection coefficient at any location x, hx, this is local convection coefficient. This is negative k dt dy at y equals 0 over Ts minus T infinity. Okay, we did this in the last class, that convection coefficient is this. So this is conduction from the surface. Okay, this will be equal to H times temperature difference, Ts minus T infinity. So you have this expression for Hx. Okay, and we can write dt dy in terms of dt d eta. I'm skipping some steps here. Okay, and then you get Hx equals k over x times 0.332 Reynolds number x to the power half times Prandtl number, I'm writing it here, Prandtl number to the 1/3. Okay, you get this. Hx equals k over x times that. We can take x over k on the left hand side, that becomes Nusselt number. So you write Nusselt number x, which is Hx, x over k, and this is 0.332 times Reynolds number to the half and Prandtl number 1/3. So this is the important relation we got. And this relation is valid when Prandtl number is greater than equal to 0.6. Okay. And the flow is laminar. See, this solution is only for laminar flow and flat plate. Okay. And we also get thermal boundary layer thickness. I'm just going to write the final expression you get. I'm skipping some of the intermediate steps. From this analysis, you also get that the ratio of thermal boundary layer thickness to velocity boundary layer thickness, delta T over delta, is 1 over Prandtl number to the power 1/3. And this again is valid for Prandtl number greater than equal to 0.6. Okay, this is the ratio of thermal boundary layer to velocity boundary layer. Okay, so see, you can write this as, because Prandtl number is nu over alpha. Okay. Nu is momentum diffusivity or kinematic viscosity, and alpha is thermal diffusivity. So this thing is equal to, you see, alpha over nu to the 1/3. Okay. And it is very easy to remember this relation. If alpha is large, okay, thermal diffusivity is large, okay, then the thermal boundary thickness is more. Okay, if momentum diffusivity is large, then the velocity boundary layer thickness is more, right? Okay, if thermal diffusivity is large, then the effect of the plate is felt up to a farther distance from wall. So thermal boundary layer thickness will be more. Okay, that's the idea. Okay. And Prandtl number for gases like oxygen, nitrogen, okay, air, all these gases is around 0.7. So delta will be almost equal to delta T. The Prandtl number is around 0.7 for gases. Okay. For viscous oils, this number can be very high. Actually, it can be even in thousands. Okay, it can even be 5,000. Okay. So what does that mean? Which boundary layer thickness will be more? Actually, velocity boundary layer thickness will be much greater than thermal boundary layer thickness, right, for viscous oils. They are highly viscous. So the velocity boundary layer is much more thicker than the thermal boundary layer. Okay. Whereas we have liquid metals, and those include, for example, mercury, sodium, okay, potassium, lead, bismuth. Okay, all these are liquid metals because they become liquid at relatively low temperature, and they have very high thermal conductivity. Okay, they have high thermal conductivity, and their Prandtl number is very small. Okay, I don't have exact numbers, but it is of the order of 0.01. Okay, Prandtl number is very small for these. Okay. Okay, that means for them the thermal boundary layer thickness will be much more than the velocity boundary layer thickness. Okay, it's very easy to remember because they have high thermal conductivity, so the effect of wall in terms of temperature will be felt up to a farther distance. So thermal boundary layer is thicker than velocity boundary layer. Okay. And liquid metals are used because they have high thermal conductivity. They are used where you want high rate of heat transfer. Okay, although they are corrosive and they are also toxic also, and they have low vapor pressure, which is advantage, and they have high thermal conductivity. Because of that, they are still used. Okay. Okay. Now we can also write expressions for average properties. The average Nusselt number up to distance x. Okay. This will be the average convection coefficient times x over k. Okay, I hope you understand the difference between the local and average values. This convection coefficient h, it varies. So again, look at the flat plate. This h is a function of x. And in the last class I discussed. So if you consider, say, this is just a laminar boundary layer, then in x direction, this local convection coefficient, it varies. It is very large here and then it decreases. Okay, that is local convection coefficient. But now we are defining an average convection coefficient. And based on that, we have an average Nusselt number. Okay, h bar x over k. You can do a very simple integration. Say this h bar for a flat plate, it will be just 1 over L integration of, this is the local, so I'm writing this as hx, or you just write as h dx as it goes from 0 to L. Okay, this is average convection coefficient up to distance L. Okay, just average of that. Okay, you can do that and then find out this average Nusselt number. It's a very simple integration, so I'm leaving that to you. But you will find that this average Nusselt number is twice the local Nusselt number. Okay. Average Nusselt number is twice of the local Nusselt number. And this is for the correlation we obtained for the Nusselt number using that correlation. Okay. And similarly, you can define an average friction coefficient, okay, up to distance x, this average. Okay. This also called coefficient of drag. This will be integral cf dx, x goes from 0 to x and 1 over x. Okay, that is average up to x. And it will turn out to be twice of the local. Okay, so averages are twice of local. Okay, averages are twice of local. Okay. Okay, now one final comment. Actually, when dealing with these equations, we considered that properties are constant, right? We said viscosity is constant, thermal conductivity is constant, but that is not true. Especially for liquids, viscosity is a very strong function of temperature. Okay, for example, for water, you change temperature from 300 to 400 Kelvin, there will be a very big change in viscosity. So there will be a big change in Reynolds number. Okay, so but these are for constant viscosity. Are they applicable? Okay, it turns out that if we use what is called film temperature, okay, we write that as TF, and this is average of surface and T infinity temperature. Okay, if we define a film temperature like this, average of the surface and fluid at infinity temperature, and read properties at this temperature, then these correlations turn out to be in excellent agreement with experimental data. Okay, so you are saying that the properties are constant, but you are reading properties. Okay, all these things, density, viscosity, thermal diffusivity, all these things you are reading at film temperature. Okay, reading at film temperature. Okay. Now, if you compare the expressions for this, for Nusselt number and the CF, okay, just compare these expressions, and you will find out that Nusselt number over Reynolds times Prandtl to the 2/3 equals CF by 2. Okay, we'll find this just by comparing them. Okay. And this thing, Nusselt over Reynolds Prandtl, this is called Stanton number. Okay, we write that as ST. So you got Stanton times Prandtl to the 2/3 equals CF by 2. Okay. And this formula has many implications. See, it correlates. Stanton number is related to heat transfer because it has Nusselt number in it, right? It is related to heat transfer. And what is this CF? It is not related to heat transfer. It is related to drag. Okay, so this is related to momentum, and this is related to heat transfer. So you can say that this represents an analogy between momentum and heat transfer. Okay, they are related. So this is an analogy. This is an example of analogy between momentum and heat transfer. And what you can do is, let us say you say that I don't want to do heat transfer experiment. I just want to do an experiment in fluid mechanics, just want to determine the drag. Okay, so you're doing experiment to find CF. And you can use CF to determine the Nusselt number. Okay, so without doing a heat transfer experiment, you are getting a Nusselt number. Is that clear? So this is an analogy between momentum and heat transfer. Okay. So this equation was valid for a flat plate. Okay, because we are discussing a flat plate. For flat plate, dP dx is 0. Okay, for flow over a flat plate, there is no pressure gradient in the x direction. So this equation, okay, this equation is applicable when dP dx is 0 and the flow is laminar. If dP dx is not 0, okay, if dP dx is not 0, okay, that will be if it is not a flat plate, say it's a cylinder or it is an aerofoil, then dP dx will not be 0. okay, because dp dx depends on the shape of the object. But let us say the flow is turbulent. Okay, flow is turbulent. It turns out that this analogy is applicable even then, okay, reasonably well. Okay, this analogy works well. Okay, so the idea is for flow over a flat plate, we can use this, whether the flow is laminar or turbulent. Okay, but if it is not a flat plate, but you have dp dx, okay, then the flow is turbulent, then also it will give you a reasonable result. Okay, and this analogy is called, it is called modified Reynolds or Chilton-Colburn analogy. Okay, that is the name of this analogy. Okay, so you can say this is method 4. We are talking about methods for getting convection coefficient. Okay, this is another method that you are doing a fluid mechanics experiment, or whatever way you determine CF, and you are using that to get Nusselt number. So this is another method. Okay, to get convection coefficient. Okay, now I will talk about one more method. This probably you are going to like because it is much simpler. So this is what we call integral boundary layer analysis. Okay, integral boundary layer analysis. This is an approximate method. And it is applicable for both laminar and turbulent. Okay, the previous one we discussed, the Blasius solution, that was an example which is applicable only for laminar. Okay, and it was not approximate, it was exact solution of boundary layer equation. Okay, now we will look at an approximate analysis of the boundary layer, and this is much simpler. Did you learn about this in fluid mechanics? Integral boundary layer analysis. Okay, it is very important actually. Okay, now consider, say again taking example of flow over a flat plate, and let us say the velocity boundary layer develops like this. This is delta. If we take a streamline outside, you know, the outside streamline that is deflected. I'm drawing a streamline because the flow decelerates, so it is going to deflect like this. Okay, this is a streamline. And if I take a control volume like this, so this is one boundary of the control volume, then the plate, and another boundary is here, and then this streamline. Okay, this is the control volume. Okay, let me call this section as section 1. Okay, this as section 2. And again, this is x direction, and flow comes with velocity u infinity, which is uniform. Okay. So see, the choice of the control volume is clever. Is there any mass flow across this boundary? No, because this represents the streamline. Okay, there is no mass flow across this. That represents the wall. Because the only mass flow is from the left section, that is section 1, and from the right, that is section 2. So you have mass flow only at these two places. Okay. And you can write by conservation of mass, you can write integral rho u dy, okay, at section 1. Okay, so this integral is from this point to this point. So this represents the mass flow rate here. Okay, integral rho u dy. I'm taking unity depth. Okay, this will be equal to integral rho u dy at section 2. Okay, that is conservation of mass. Okay. Okay, now let us look at the momentum equation. And I'm drawing this control volume again. So this is the streamline. Okay, this is the left section, section 1. This represents the plate surface, and this is section 2. Okay, that is the control volume. Now, you remember from Reynolds transport theorem from fluid mechanics, okay, we get a momentum equation that is applicable for control volume. So what will be momentum in here? Okay, from the left face, that will be integral of rho u square dy. Okay, that is momentum that enters at 1, right? Integral of rho u square dy. Momentum that comes out from section 2, that is also integral rho u square dy, but integration is at section 2. Okay. And there is no momentum exchange here and here because there is no mass flow. Those are the only places where we have momentum transfer. Okay. Now, apart from this, what are the forces acting? See, you have pressure force and viscous forces, right? Okay, we neglect gravity, that is a body force, but at the surface you have pressure and viscous forces. But pressure is uniform throughout. Okay, so that will cancel. Okay. Viscous force, is there any viscous force here? Okay, no viscous force because there is no velocity gradient here. This is outside the boundary layer. Outside the boundary layer you don't have any velocity gradient, so there is no viscous force here. Okay. What about this one? Actually, there is viscous force here because you have velocity gradient in the x direction that is related to del u del x. You have a viscous force, but that is negligible. Based on boundary layer approximation, del u del x is very small. Okay, so we neglect that. Okay, any force here? Okay, you have that force, that viscous force because of the plate. Okay, that I'm writing that as in this direction, we call that drag. Okay. So now we can write the momentum equation for this control volume, which will be force in x direction. Force in x direction is negative d. That is force in x direction equals net momentum flux in the x direction, which will be integral rho u square dy at section 2 minus integral rho u square dy at section 1. And this I can write as integral rho u square dy minus integral at section 1. See, at section 1 u is same as u infinity. Okay, it is uniform because that is x equals 0. U is u infinity. So I can write this as u infinity square, or I can take one u infinity outside, and inside I can write rho u dy. Okay, because u square, I can write that as u infinity or u infinity square. At section 1 u is just u infinity. Okay. And integral rho u dy at section 1 is same as integral rho u dy at section 2. Okay, that is conservation of mass. Okay, so I just rearrange these terms, and you can write, you will get this expression. Just rearrange this, you will get d is rho u infinity square times integral at section 2, I'm not writing section 2 at this point, times u over u infinity times 1 minus u over u infinity dy. Okay, this integral is at section 2 because we got an expression for drag. Okay, now see, this u over u infinity is 1 outside the boundary layer, right? So this integral this integral will be 0 outside the boundary layer. 1 minus 1 will be 0. So I don't have to integrate over the entire section 2. I have to just integrate from 0 to delta. Okay, y goes from 0 to delta. Because outside delta, this integral is 0. Okay, so let me write this expression again. So you get d is, I just want to highlight this, rho u infinity square times integral u over u infinity of 1 minus u over u infinity dy, y goes from 0 to delta. So this is the expression that gives us drag. So you see, we did not solve any differential equation. This is integral analysis. Okay, when you do differential analysis, you get the details of the flow everywhere in the domain. Okay, when you do integral analysis, you get some overall thing you are looking for. So if you are looking for drag, we are not looking for all the details of the flow. This is integral analysis. And this term here, this whole integral term, okay, this is called momentum thickness. Okay, momentum thickness of boundary layer. And generally we use symbol theta for this. So you can say the expression is d is rho u infinity square theta. Okay, so we still don't have drag. We are interested in drag. Okay, but see, if you know the velocity profile in the boundary layer, what is this u over u infinity? You can integrate this. Okay, and it turns out that we can assume any reasonable velocity profile. That is why this analysis is approximate. We are going to assume a velocity profile in the boundary layer. Okay, it has to be reasonable in the sense it has to be 0 at the wall, u infinity at the boundary layer tip. Okay, and then integrate this expression and see what we get. And you will get the result which is very close to the exact analysis, that Blasius solution. Okay, so this approach is very powerful. You are not actually solving the differential equation, but very simple integral analysis and you will get it. Okay. Now, before you do that, let me explain one more thing. Okay, let us say this distance is x, and then we make a differential change in this. This is dx. And say the drag up to distance x was d, and drag on this section here is dd. Okay. So you can write this dd. It will be equal to the local shear on the plate tau s. This represents on this depends on x times dx. So this gives you tau s is dd over dx. Okay, tau s is dd over dx. So we can write an expression tau s equals, we have expression for d, just differentiate this. It will become rho u infinity square d theta dx. Okay, so that is the local shear on the plate, tau s. And you know tau s is also equal to mu del u del y at y equals 0. Okay, that is by definition it is equal to that. Okay, so we are just going to use this. We will assume a velocity profile and use this, and you will see it gives us tau s, and once you have tau s you have cf, because cf is just a non-dimensional form of tau s. Okay, so you'll get cf and you will also get boundary layer thickness. Okay, so this approach is very powerful. Okay. Now there are different ways to assume the velocity profile. I'm going to do one of those which is relatively more rigorous. So if you assume, let us say u over u infinity, it is say a plus by plus cy square plus dy cube. Okay, so it's a polynomial, third order polynomial. And see what are the conditions that u has to satisfy. U at y equals 0, u is a function of y, u at y equals 0 is 0 at the wall. Okay. U at y equals delta, what this thing will be? It will be u infinity, right? It will be u infinity. Okay. Along with this, del u del y at y equals delta will be 0, because outside boundary layer there is no velocity gradient. This will be 0. And you also have one more, that is del square u. Actually, you can write d square instead of del square, because u is just a function of y here. Okay. Del square u over del y square at y equals 0 is also 0. This comes from looking at the boundary layer equation, because at the wall u is 0 and v is also 0, so del square u over del y square has to be 0. Okay, you get this by the boundary layer, by the momentum equation, you get this. So we have to satisfy, okay, these four conditions, and it has four constants a, b, c and d, so you can get those constants, and you get this u over u infinity equals 3 half y over delta minus half y over delta cube. Okay, get this. Okay, see, this is an assumption, this velocity profile, but it satisfies the boundaries. Okay, actually we could have taken another also. For example, you can take a linear profile. Okay, it just varies linearly with y over delta. That also gives a reasonable answer. Okay, so we take this profile and substitute this in this equation. Okay, because you have a profile for u over u infinity, substitute that in this equation, integrate this, you will get what this theta is. Okay, just very simple integration, you get what this theta is, and then you can differentiate that d theta dx, and you can also write del u del y at y equals 0, but that thing is going to be based on this profile, what will be del u del y equals 0. Okay. So idea is you will get what this is and what this is. Let me just write that finally. Okay. So you get so what you get is tau s equals rho u infinity square d dx of 39 delta over 280, and this equals based on mu du dy at y equals 0 equals 3 half mu u infinity over delta. Okay, you get this. Okay, now say look at these two. Okay, this is an equation that has delta. Okay, this equation, it has c d delta dx, and right hand side has delta, so we can integrate this. Okay, it's a simple integration, and delta at x equals 0 is 0. Okay, that is the beginning of boundary layer, and say delta at any x equals delta. Okay, so if you integrate this, you get an expression for delta. You'll get delta is 4.64x over square root Reynolds number x. Okay. Now compare this with the exact solution, that Blasius solution, that was 5x over square root Reynolds number x. So see how close it is. Okay. But it is a very simple analysis. Okay. You are writing the integral boundary layer equation, and then you are just assuming a velocity profile. That's all that gives you this. And you also get expression for tau s. You can substitute the value of delta here, that gives you tau s, or in non-dimensional form, the value of CF you get is 0.647 over square root Reynolds number x. Okay, this is very close to the exact solution you get from the Blasius. Okay, so that is integral boundary layer. Okay, now let us look at energy equation. So we have to first solve the momentum before we do energy, because they are coupled. In the energy equation you have u and v. Okay, do the same thing with energy. Now okay, this is the plate, and let us say this represents delta and this is delta T. Okay, they are not equal, one can be larger than other. Okay. And again we take, let's say a streamline is like this, and we take a control volume, okay, between this face, okay, this face, plate and the streamline. So this is section 1, this is section 2, and on this we are going to just write the energy equation. Okay, now let me draw this control volume again and we'll write what energy terms are. So this is the control volume. The energy you have is, there is advection here, okay, and that term will be rho u dy. Okay, this is mass flow rate, right? Okay, density times velocity times area. This is mass flow rate. Multiply this with specific heat times temperature. Okay, this is the rate at which enthalpy is advected at section 1. Okay. At section 2, same thing. You have rho u cp t dy. Now this is at section 2. Okay. Here there is heat transfer between the plate and the fluid. Because of that, I'm just indicating that as Q. Okay, this is heat transfer from the plate to the fluid. There is no conduction here because temperature is uniform here. There is no temperature gradient in the x direction. There will be some conduction here, but that will be negligible. Okay, you neglect the effect of dt dx, that is boundary layer approximation. And any energy coming from this? No, because this is outside the boundary layers. There is no temperature gradient here, and there is no mass flow across this boundary. So that's all. Okay, so energy balance on this will be Q equals integral rho u cp t dy at section 2 minus rho u cp t dy at section 1. Okay, that is Q. Just energy balance on this. Okay. Now we'll do the same trick that we did with the momentum equation. So see this thing. Okay, let me just expand this term first. This integral rho u cp t dy at section 1. I can write instead of t infinity because temperature is t infinity there. Okay, there is no effect of boundary layer at section 1. This is just t infinity. You can pull cpt infinity outside of integral because that is a constant. And integral rho u dy at section 1 is same as integral rho u dy at section 2. Okay, that is mass conservation. Okay, so this equals, what you get is this equals integral rho u cp t infinity dy at section 2. Okay, that is what you get, and you substitute this there, and the expression for Q becomes rho cp integration from 0 to, we have to integrate it only up to delta T, because beyond delta T this integral becomes 0 because temperature is T infinity. Okay, of u T minus T infinity dy. Okay, this is Q. Okay, now again say this is plate, and say from distance x, from length x, heat transfer is Q, and now we take a differential length. Okay, this length is say dx, and heat transfer from this is dq. You can write dq will be Okay, q double prime, this is flux from the surface. Okay, local flux from the surface which depends on x times dx. Or you can write q double prime is dq dx. Okay, q double prime is dq dx. Okay. And see, q double prime is also equal to h times ts minus t infinity. Okay, it is also equal to that. So we are just going to do that. And actually this is also equal to negative k dt dy at y equals 0, right? Okay, this thermal conductivity of fluid. Okay, so this is the surface heat flux. You can write this in terms of convection coefficient, in terms of temperature gradient, and this is dq dx. Okay, we have this expression for q. So let me write it finally in this way. So you have dq dx equals negative k del t del y at y equals 0, and this is rho cp d dx of integral 0 to delta t of u t minus t infinity dy. Okay, so this is the expression we were looking for. Okay. This will give us the value of delta t and also this whole thing. Okay, we can use that to get Nusselt number or convection coefficient. Okay, so it is analogous to what we did with the momentum equation. Okay, okay, now the approximation. The approximation will be, we assume a profile for temperature. Okay, that is the approximation. Okay. So assume like T is A plus BY plus CY square plus DY cube, and along with this temperature has to satisfy these conditions. Temperature at y equals 0 is Ts, temperature at y equals delta T is T infinity, and temperature gradient, just writing dt dy at y equals delta T is 0, and d square T over dy square at y equals 0 is 0. It has to satisfy those conditions, and based on these you can get these constants a, b, c and d, and you get this profile T minus Ts over T infinity minus Ts is 3 half y over delta T minus half y over delta T cube. Okay, you get this. So see, this is our assumption. Okay, this is a reasonable temperature profile which satisfies the boundary. We can substitute this temperature distribution in this equation now. Okay, substitute that in this equation, and we have a formula for u also, the velocity profile we assumed for u, and integrate this thing. Okay, and then apply this formula. So I'm just going to write finally what you get. Okay, so see, mathematically there are a lot of steps, but in terms of concept I wanted to introduce this because it is a very powerful technique in terms of concept. You are not solving the differential equation, you are writing an equation for an integral control volume. Okay, and then just make the only approximation is you are saying that this is the temperature distribution or this is the velocity distribution in the boundary layer. So finally, by solving this, what you get is 1 over 10 u infinity. This is zeta cube delta d delta over dx equals alpha. Okay, where this zeta is delta t over delta, and there is an approximation actually in deriving. We assume that this thing is less than 1, so we neglect the square terms and the fourth order terms of this. Okay, when we derive this equation, it is based on less than 1. Okay, see, we already have an expression for delta. Okay, so this gives you an expression for delta t, and you get delta t over delta equals 0.976 over Prandtl number to the 1/3. Okay. Now compare this with the exact solution from Blasius. Okay, that was same thing. Instead of 0.976, that was 1. Okay, the answer is very close. And you also get convection coefficient from this, or in terms of Nusselt number, you get Nusselt number is 0.33, Reynolds number to the half, okay, Prandtl number 1/3. Okay, compare this also with what you get from Blasius, and it is, this one is actually almost exact. The agreement is excellent. Okay, so that is integral boundary layer analysis. Okay, you like this one or no? At least you like it better than Blasius, right? You don't have to solve the differential equation. Okay, and this has been applied for many situations. Okay, because you don't have to solve uh, the boundary layer equations actually. Okay, the only thing is that velocity profile has to be reasonable. Okay, for turbulent flow, if the flow is turbulent, okay, we can still use this approach. It turns out that for turbulent flow, velocity varies with y to the power 1/7. Okay, that is the velocity profile. You know, for turbulent flow, so this is flat plate. In the turbulent region, velocity profile is like this. The gradient is very sharp at the wall, and then you have relatively flatter. Okay, so it is of this. Okay, so when you assume a velocity profile and it is turbulent, you assume something like this. Okay, and then do the same analysis. So what you get, the answer will be applicable for turbulent flow. Okay, that's the idea. That is integral approach. Okay. Okay, I think I'm going to continue. We have been discussing the topic of convection, and I discussed that there are 5 methods you can have to determine the convection coefficient. Okay, again, just for review, we can use CFD, and we have the governing equations. That is one. We can use dimensional analysis along with experiments. So we'll have a correlation for heat transfer. We can do an analysis of the boundary layer equations. Blasius solution was an example of that. Or we can use the analogy between heat transfer and momentum transfer. So that was like Reynolds, modified Reynolds analogy, or which is also called Chilton-Colburn analogy. Or we can use the integral boundary layer analysis, which is an approximate method, but it is applicable for laminar and also turbulent boundary layer. I'm going to talk a little bit more about the theory, and we will revisit the dimensional analysis. When we do dimensional analysis, we have 2 options. So one option is we write down on what parameters the phenomena depends. For example, if we take, let us say, the case of flow over a flat plate, and we are interested in, say, the average convection coefficient. So you can write down that average convection coefficient. It will depend on all the parameters that you think are important. Like there will be density, okay, velocity of fluid, okay, then the length of the plate, okay, dynamic viscosity, say thermal conductivity of the fluid, thermal diffusivity of the fluid. So like that, okay, we list all the parameters. That is one option, and based on this we can come up with the non-dimensional parameters. Okay. But there is a possibility of making a mistake in this method. For example, we might miss some of the parameters which are important, or we we might end up including parameters which are not important and make it unnecessarily complicated. Okay. So the another approach is to start with the governing equations, and that's what I'm going to discuss in this lecture first. So if we write down again the boundary layer equations, the momentum equation is in the x direction, u del u del x plus v del u del y equals negative 1 over rho. This thing is just dp dx plus nu del square u over del y square. Okay, this is the equation. And the energy equation, that is u del t del x plus v del t del y equals alpha del square t over del y square. So these are the equations these are the boundary layer equations, because we did not include some of the terms which are negligible in the boundary layer. And we can non-dimensionalize this equation and then see what parameters we get. So that's what we are going to do. So non-dimensionalize the equation. And when we non-dimensionalize, we can define non-dimensional x star as x over L, non-dimensional y star as y over L, non-dimensional velocity u star, we can define this as u over a reference velocity, and this reference velocity can be u infinity. For flow over a flat plate, it will just be u infinity. Okay, similarly v star as v over this reference velocity, non-dimensional temperature as T minus Ts over T infinity minus Ts, and non-dimensional pressure as P over rho u ref square. Okay. So if we non-dimensionalize the boundary layer equation considering these, it is very simple to do that, but the equation that we get is you get u star del u star over del x star plus v star del u star over del y star equals negative dp star over dx star plus 1 over Reynolds number based on L times del square u star over del y star square. Okay. So that is the x momentum equation. So you see, in the non-dimensional equation we got this parameter Reynolds number. Okay. And similarly the non-dimensional energy equation, that becomes u star del t star over del x star plus v star del t star over del y star equals 1 over Reynolds number L times Prandtl number times d square t star over d y star square. Okay, we get this equation. So we got Reynolds number and Prandtl number automatically by non-dimensionalizing the governing equation, the boundary layer equation. We got these parameters. Okay. And we can also write boundary conditions in terms of u star, v star and t star. So those, let me write down, those are just common sense. U star at x star when y is 0, this will be 0 because velocity at wall is 0. Okay, u star at x star but y star is infinity, this will be u infinity. But u infinity can be a function of x. Okay, if it is not a flat plate, then u infinity will be a function of x. For example, say you have an object like this. Okay. So flow velocity here says u infinity. Now as it flows over it, u infinity is going to change. The velocity outside the boundary layer, it will be a function of x. So I'm writing this as u infinity x star over the reference velocity. Okay, this reference velocity we can take as u infinity upstream, so in this region. That is the velocity when y is infinity. Okay. And in terms of temperature, you'll get T star at the surface will be 0 and T star at y star of infinity will be 1. It will approach the free stream temperature. Okay. So those are the non-dimensional. You see the non-dimensional equations for momentum and energy and non-dimensional boundary conditions. Okay. So based on this, you can write u star will be a function of, we are not actually solving these equations, but we just want to see what u star will depend on. So if you look at this, you see, looking at this equation, u star is a solution of this equation. It will depend on x star, y star, pressure gradient and Reynolds number. So you can say u star is a function of x star, y star, Reynolds number and the pressure gradient. Okay, the non-dimensional pressure gradient. We discussed this previously, that this pressure gradient is due to the shape of the object. And if the objects are geometrically similar, okay, then we don't have to consider this because this term is same. So u star is a function of x star, y star and Reynolds number. You can say that, okay, if the objects are geometrically similar. Okay. Now based on this we can write, see, tau s, this is the shear at the wall, which is given as mu del u del y at y equals 0. So this becomes mu in terms of u star and y star. This becomes mu u ref del u star over L times del y star at y star equals 0. And this you can write as, actually not this term. If we non-dimensionalize this and write CF, this is a local friction coefficient, as tau s over half rho u ref square, and substitute for tau s from this, you will get this equals twice over Reynolds number times del u star over del y star at y star equals 0. Okay. And we can write this as twice over Reynolds number. Now see, this del u star over del y star at y star equals 0. We wrote u star is a function of x star, y star, Reynolds number and this pressure gradient. So if we differentiate this del u over del y and take the derivative at y equals 0, that will be a function of x star, Reynolds number and this pressure gradient. It will be some function. We are not interested at this point in getting what that function is. So there is going to be that term here. Let me write it again. So you will get CF is twice over Reynolds number times some function, let us call this f1, of x star, okay, Reynolds number, and also you have this pressure gradient which depends on the shape of the object. Okay. But I'm not going to consider this one from this point because this will be same for geometrically similar objects. If you have same Reynolds number, then this term will be same, so we don't have to consider this. Okay. Now similarly, if you look at the energy equation, see, this is the energy equation that gives us T star. Based on this equation, you can write T star is some function, let us call this f3. Okay. It is some function of x star, y star, and you have Reynolds number in this. So Reynolds number, there is also Prandtl number, and you also have velocity in this, and velocity also depends on pressure gradient. So dp star over dx star. Okay, but this we are not going to consider. Okay, so T star is a function of this. You can write it like this. Okay. Now the convection coefficient H, that is negative k del t del y at y equals 0 over Ts minus T infinity. Okay, this local convection coefficient. Okay. And you can write this in terms of T star and Y star, and you will get this equals Kf, this is thermal conductivity of fluid, over L, this was also Kf, times del T star over del Y star at Y star equals 0. Or you can rearrange these terms. You can write HL over Kf, okay, which is Nusselt number based on L. This equals del T star over del Y star at Y star equals 0. Okay, we get this. Now look at this temperature. If temperature is given by this function, we differentiate this with respect to Y star and take Y star equals 0. So the result will be, you'll get, it is some function, say f4, of x star, Reynolds number, and Prandtl number. Okay, some function of x star, Reynolds number, and Prandtl number. So see, these are the results we were looking for in terms of non-dimensionalizing the boundary layer equation. Let me summarize it. We got Cf is twice over Reynolds number times some function of x star and Reynolds number. And we got Nusselt number is some function of x star, Reynolds number, and Prandtl number. Okay, so that is another approach. When we want to do a dimensional analysis, we can write down all the parameters and determine what the non-dimensional parameters are and what is going to be the form of the correlation. Okay. Or other is we can non-dimensionalize the governing equation. That is what we did here. And if you want to write average values, see CF average. So we are going to take an average of this. That will be 2 over Reynolds number times some function, say let us call that as f2. So it will, if you integrate this function over the length, you will get, there won't be any x star then, it will be some function of Reynolds number. So the average CF depends only on Reynolds number. Okay, that's what we get. And similarly, average Nusselt number. This will be some function, say f5. You get that by integrating this expression. It will be some function of Reynolds number and Prandtl number. So that's the idea. So for external flow, like for flow over a plate or flow over a cylinder, the important parameters are Reynolds number, Prandtl number, and convection coefficient is given in terms of Nusselt number. Okay, so this we got by non-dimensionalizing the boundary layer equation. Now we are going to look at several correlations for turbulent flow, because for turbulent flow we don't get answers based on theory. Like the Blasius solution and the Nusselt number we got for flow over a flat plate, that was for laminar flow. Now if we have turbulent flow, okay, for turbulent flow, and we are talking about flat plate. We have this experimental correlation that CF is 0.0592 times Reynolds number to the negative 1 over 5. And this correlation is valid for Reynolds number greater than the critical Reynolds number, so that the flow is turbulent, and less than 10 to the 8. Okay, so this is an experimental correlation. Okay, for flow over a flat plate, the local friction coefficient in the region where flow is turbulent. Okay, and we also have an expression for delta. So in the region where boundary layer is turbulent, you get delta is 0.37x over Reynolds number to the 1 over 5. Okay, when the boundary layer is turbulent. Okay. Now if you compare these relations with the relations we had for laminar, see CFX for laminar, it varies with x to the power actually negative half. And if you look at the correlation for turbulent, it varies with x to the negative 1 over 5. Okay. So the idea is friction coefficient in the laminar region, it decreases at a faster rate than it decreases in the turbulent region. Okay, because here it is x to negative half, here it is x to negative 1 over 5. So let me write here. So the rate of decrease of CF is more rapid in the laminar region than in the turbulent. Okay. Now if you look at the boundary layer thickness, delta for laminar flow, it increases with x to the power half. But for turbulent, and we are talking about flow over a flat plate, it increases with x to the power 4 by 5. Okay, so you have the opposite result, that the boundary layer thickness in the turbulent region grows at a faster rate than laminar. because in the laminar region it increases with square root of x, and this is x to the power 4 by 5. So turbulent boundary layer increases at a faster rate. Okay. And another point is, if we compare delta and delta t, you see the ratio of delta to delta t, we talked about this previously. This was Prandtl number to the power 1/3. Let's see if that is right. Yeah, it was Prandtl number to the power 1/3. This was for laminar. For turbulent flow, the difference between delta and delta t is much smaller. So you can say delta and delta t, okay, they are similar for turbulent flow. Unless Prandtl number is too low or Prandtl number is too high, okay, they are going to be of similar order. And reason for that is, when the flow is turbulent, then the role of molecular diffusivity is small and the turbulence plays a dominant role. Okay. Whereas when the flow is laminar, then the molecular diffusivity is the only mechanism that is playing the role. So it is going to depend on the ratio of nu and alpha, that is Prandtl number. But in turbulent flow, turbulent transport dominates and molecular viscosity does not play that important role. And the turbulence mixing is similar whether you are talking about the temperature or momentum. Okay, that is similar. So they are of the same order. Now finally, for turbulent flow, we can use this expression that we have for CF. So this is the expression for CF, and if you remember, we can use this expression along with the Reynolds analogy. That was Stanton number times Prandtl number to the 2/3 is half CF. Okay, that was Reynolds analogy. So we use this analogy along with this expression for CF. So we get an expression for Nusselt number. That expression is this local Nusselt number equals 0.0296 times Reynolds number to the 4 by 5 times Prandtl number 1/3. And this expression is valid for Prandtl number in the range of 0.6 to 60. So we get this expression. For local Nusselt number in the region where boundary layer is turbulent. Okay. Okay. So again, you can see, based on this expression, the local convection coefficient in the turbulent region, okay, it varies with, you have say x to the power 4 by 5 here, and then you'll have x coming down here when you consider the convection coefficient. So it will be x to negative 1 over 5. Okay. Whereas the variation of hx in the laminar region, you had expression for that previously, it was like x to the negative 1 over 2. Okay. So again, you can say that hx decreases at a faster rate in the laminar region. Okay, than in turbulent. Because in the laminar region it decreases with x to negative half, which is faster rate than x to negative 1 over 5. Okay, so that's the idea. Okay, so see, in this case, to get this Nusselt number, we used the Reynolds analogy, which is analogy between momentum and heat transfer. Okay, now when we have a mixed boundary layer, so the mixed boundary layer is, the boundary layer is laminar up to this point. Say this is XC. And then there is transition, and then it becomes fully turbulent. Okay. But for simplicity, we assume that there is no region of transition. So it is laminar up to this point, and at this point it becomes fully turbulent. So it is going to grow at a faster rate. Okay. So this is the region in which boundary layer is laminar, and beyond this it is turbulent. If we are interested in the local convection coefficient, then in the laminar region you will use the formula that is applicable for the laminar region. And let me write that formula again. That was Nusselt number. This local Nusselt number is 0.332 times Reynolds number to the power half and Prandtl 1/3. Okay, this is the formula. And in the turbulent region, for local Nusselt number, the formula for the turbulent boundary layer is applicable, and that formula is Nusselt number is 0.0296 times Reynolds number to the 4/5 times Prandtl 1/3. Okay, these are the formulas, and they have the region of Prandtl number in which they are valid. Okay, this formula is for Prandtl number greater than or equal to 0.6, and this is for Prandtl number greater than 0.6 and less than 60. Okay, so if you are interested in the local Nusselt number or local convection coefficient, we can use these formulas. But if we are interested in average, now the part of the boundary layer is laminar and the part is turbulent. So the way we average is going to be different. Let me explain that. So if you want to write an expression for average Nusselt number, okay, over length L, this will be average convection coefficient times length over K. Okay. Now how to get this average convection coefficient? This H bar over length L. If the boundary layer is mixed, so this will be integral hx dx as x goes from 0 to L times 1 over L. We have to basically integrate this expression. Okay. If the boundary layer is mixed, it will become 1 over xc. Up to distance xc, boundary layer is laminar. So you are going to use the h value for laminar. Sorry, this won't be 1 over xc. Let me change this. It will still be 1 over L. Or let me write it again. This will be 1 over L times integral from 0 to xc of h laminar dx plus from xc to L of h turbulent dx. Okay. Because the boundary layer is laminar up to xc, and from xc to L boundary layer is turbulent. and then this represents an average of that. That will give us average convection coefficient. Okay. I'm not going to do the math, and I highly recommend that you work out this integral and you verify that based on this, when you write down expression for average Nusselt number, after integrating this expression, you write average Nusselt number, that turns out to be 0.037 times Reynolds number to the power 4 by 5 minus A times Prandtl number 1/3, where A is 0.037 times critical Reynolds number to the power 4 by 5 minus 0.664 times critical Reynolds number to the power half. Okay, you get this as average Nusselt number. Okay, and see, the thing here is it is applicable when you have mixed boundary layer. Okay, so the part is laminar, part is turbulent. If you don't have mixed boundary layer, then it is different. The value of REC, okay, can be anything. The default value, if nothing is given, we take as 5 times 10 to the 5. So this is the Reynolds number at which flow becomes turbulent. Okay, that is the default value we take. And based on this, you get the value of A is 871. Okay, that is the default. But let us say the problem gives you a different value of critical Reynolds number. Then you'll have to substitute that number here, that gives you A, and then you can use this expression for average Nusselt number. Okay. A special case is if the boundary layer is turbulent throughout. Okay, the boundary layer is turbulent throughout, so you have, say, flow over a flat plate. And let us say you have, say, some wires here. So when fluid flows over these wires, okay, these introduce turbulence, and it is possible that boundary layer is turbulent right from the beginning. Okay. So in this case, what is XC? XC is 0 because boundary layer is turbulent right from the beginning. So the critical value of X at which it becomes turbulent as is 0. And you get REC, the critical Reynolds number is 0 based on XC. So in this case, the value of A is going to be 0. And your average Nusselt number will be just this thing times Prandtl number to the 1/3. Okay. So that's the formula when you have mixed boundary layer. Okay, so we are done with the discussion for flow over a flat plate.